As you can see, I've picked an S deflector there. The second one is going to go to this maroon test, this maroon event I mean, so I'll just pick this planar deflector for that. And the third test is actually going to go over here to this universal deflector. There we go. So you can see that actually as I pick each deflector, the name of the actual operator changes to reflect that. So you got S deflector, deflector, new deflector. Now, if I actually get our source, change the size of the icon slightly, so it's actually quite a bit larger, covers our area. Let's just move it over here a little bit so we don't waste particles falling off into space. There we go. Now then, let's see what happens if I scrub the timeline. What we should actually get is particles should collide with each one of these deflectors. But don't forget, in the U deflector's case, it's actually going to use the teapot geometry, not this little shape here. And you should find our particles bounce off and change color. So there we go. The S deflector, you can see they're bouncing off. And I don't know if you can see it there on the teapot. I think the teapot's mustard colored. So I'll just make that something a little bit more vivid. Let's go for let's say bright red, and we'll also make them into a bigger shape like circles. There we go, so we've got a circle there. So you can see that's actually hit the teapot and bounced off. And you can see these planar ones, we'll turn those into something different as well. We'll go for triangles. And you can see the triangles are actually there as well. So you can see we have 3 different events going on here, and the tests are actually passing the particles out to each one of those different events based on the deflectors that they're using. So there you go, you can see it's very flexible in what you can actually do with it. Now, something you could do is, let's say you didn't want to have different events for all the particles that collide, you just simply want them to collide and be sent to another event. You can actually get rid of these other tests, and what you could do is you can actually, if we have a look at this one, we just have the S deflector. So if we actually scrub now, they'll collide with a spherical deflector here, but you'll see they won't collide with anything else, they'll just carry on. So you can actually just add the other ones to this test as well. There we go, we've added all 3, S deflector, deflector, new deflector, and now if I press play, you'll see it collides with all the objects, which is great. Now that we've done that, let's have a look at the actual parameters for the 3 different basic deflectors which we've actually got here. Each offers basically the same parameters and features as the others in the set, and you can actually see that by clicking on them. You can see we've got bounce, variation, chaos, friction, inherent velocity, and you've got a diameter. For the planar deflector, you've got the same values, except you've got width and length to actually define the area of the rectangle. And for the U deflector, you can see again you've got the same parameters. You've got bounce, variation, chaos, friction, inherent velocity. You've also got icon size, and that's just a display option just to make the icon easier to pick. But you can actually see the collision surface itself is actually based on a pick object, and you can see the pick objects here. There it is. So we've got the teapot there picked as the object to use for that U deflector. So let's have a quick look at the actual parameters and see what each one does. The first one is actually bounce, and if your collision test is actually set to bounce, this parameter defines just how much speed the particle maintains after the collision. With a value of say 0%, the particle will not bounce at all and will actually move parallel with the collision surface. Whereas if you use a bounce value of say 100%, the particle will lose no speed whatsoever. Actually, when I say 100%, you can see that the values it's using here is 0 to 1. So 1 actually represents 100% bounce. A value between these two extremes will yield real-world results, with the exact value needing to reflect the material being simulated. For instance, high values for hard rubber, lower values for stone, and even lower values for soft wood and so on. Note also that you can have bounce values that actually go above 1, which will actually result in your particles gaining speed after the bounce rather than losing it. So you can actually see that here. If we go down, you can see how particles are bounced off. If I look at the planar object, you can see that we've got a bounce value of 1. If I reduce that, you'll actually see that the particles move back towards the plane. And if I put it to 0, you'll see that they actually stay